Is that all right? Okay. In the everyday aspect of daily life, we commonly use our hand to manipulate a range of objects, performing complex tasks with ease. To truly understand human behavior, it is essential that AI can comprehend the intricacies of these hand-object interactions. This video above demonstrates the process of a person completing a certain manipulation task. For example, prepare a bowl of hot sweet fruit tea. From the execution path below, we can see that this task process has several units. For example, cutting, unscrew the container lid, pour, and so on. Within each unit, the subject either interact with the different objects or facilitate the different functions of the objects. We are motivated to collect this unit as primitive tasks and obtain decomposition of this task as a complex task into this unit. One thing to observe is that the complex task manipulation tasks are structurized. They can be decomposed into a smaller task. A quick example is to decompose the complex task into several steps, which is common in recipes, in directions, or user manual. To gain better understanding of interaction in the complex level and support further planning applications, we need to pick up a decomposition scheme that breaks down this complex manipulation task into a series of a repeatable unit. One potential decomposition method is to focusing on the affordance of the object itself. To gain definition of the affordance-based interaction, we first need to analyze the object's affordance and find a good representation for this affordance. A feasible criterion is to look for the minimal interaction to fulfill those affordances, so that we could keep the building units for the complex task unique and compact enough. A further look at the complex task decomposition shows that the order of the building units is important. The order constraints hint us to investigate the dependencies of the affordance fulfillment, which is crucial in the task completion. Okay, in summary, the structure of a complex task leads us to seek a decomposition strategy. The object's affordance fulfillment provides us the solution, and the dependency orders ensure that the correctness of the decomposition process. Before diving into the OakInk dataset 2.0, let's take a moment to review the OakInk version 1. At the CVPR 2022, we introduced the version 1 with a primary focus on the affordance-based human grasp. For instance, consider a scenario involving a camera and the user's intention to take a picture. In such interaction, human typically employs only a limited set of grasp poses that align with the affordance presented by the object, the camera. To execute the affordance-based interaction, one must possess the fundamental understanding of the object functional components, such as the lens, the handle, and the body of the camera. In the OakInk version 1, we started by recording the human's grasp demonstration based on a intended action. Subsequently, leveraging a database containing thousands of distinct camera models, we developed a pipeline to transfer the human grasp, demonstrating on the camera instance to apply to all of those objects. This pipeline is called TINK, an abbreviation for the interaction post-transfer. To efficiently and accurately record human demonstration, we have developed a motion capture platform consisting of 8 infrared cameras and 4 RGBD cameras. Then, we invited 12 subjects to perform affordance grasp given the intention and the object description. We also recorded 2 humans handing over an object, which involved 2 hands interacting with one object with 2 different intentions. For the interaction transfer pipeline, we will use the context consistency to guide those post-transfer. Specifically, given a human demonstration plotted on the left, we want to transfer the post from the source to the target on target camera, for example, on the right. We first use the implicit shape interpolation to find a path from the source to the target object. We then decode several landmarks on the path and mapping the context consecutively. Finally, we optimize the context and post consistency to generate the final graph. After the context-guided post transfer, the output result meets our requirement. I will show some examples. Okay, wait a second. So video. Besides the OakInk version 2, the academic community has numerous datasets in the hand-object interaction research. For instance, the OakInk, the HOI4D, OakMan, affordance, assembly hand, application, and so on. In conclusion, there are two types of existing datasets for hand-object interaction. The 3D hand and object dataset focusing on the 3D geometry, and the 2D dataset focusing on the actions and the tasks. Dataset like the graph, HOI4D, OakInk, and OakInk contain diverse dynamic interaction, yet they do not cover the affordance-based interaction in the complex manipulation task. For the dataset like OakMan, the OakInk shape, and very recent affordance, they focusing on the static interaction of the pose, but still lack the relationship of the affordance and do not study the complex manipulation task. 2D video dataset are large scale and often contains annotations for affordance and object-object relationships. However, also the lack of 3D grounding hinders their application in the 3D understanding. To this end, the OakInk2 is proposed. OakInk2 collects demonstration of the primitive task as a minimal unit to fulfill each object affordance unit, and collects the demonstration of the combined task, combine of the primitives, as the initiation of the long-term complex manipulation of objects. Now, it is time to introduce the 2.0 version of the OakInk, a dataset of the embodied hands-object manipulation in a long horizon complex task manipulation. The introduction of our OakInk version 2 will contain 3 sections. The initial section will concentrate on the interaction acquisition process of the OakInk 2, encompassing the definition of the primitive task and the decomposition of the combined task. The interaction acquisition process itself is further subdivided into 3 stages. First is the scenario construction. The second is acquisition of the primitive task. And the third is the decomposition of a combined task. I will divide this diagram into 3 segments and discuss each of them. The first stage is scenario construction. We invite annotators to select a cluster of objects based on their coexistence from the large collected object repository. Upon identifying the objects clusters, we construct the scenarios for manipulation tasks. For example, a kitchen table. Then we ask annotators to propose complex manipulation tasks using the objects in the scenario cluster. For example, prepare a hot drink. At the second step, acquisition of the primitive task, we ask the annotators to evaluate the object within the scenario and assign affordance attribute to it. Each affordance attribute contains a specific part segmentation, like the blade, and a phrase table to discuss the function of the blade. Then, a primitive task is designed as the minimal interaction to fulfill this affordance attribute. The last stage is the acquisition and the decomposition of the combined tasks. Combined tasks are proposed to implement the specific complex manipulation targets in this scenario. The expert, for example, ourselves, instantiate the target with a specific descriptions, and then ask the subjects how to accomplish the combined task. For example, given the description of the thing and the target, ask the subject how to fulfill the target. Then the subject reply with the interaction process as the answer using the available primitive task. For example, I will use the knife for cut something. I will use the bottle for do something. This answer is summarized into the decomposition of the combined task, and the dependency of this constituent primitive task are organized into a directed graph. After this process is complete, the whole course of the human demonstration will be recorded. The second section is the dataset capture and the statistics. The data capture platform contains two major components: the optical mocap system for collecting the pulse and the multi-camera system for capturing visual information within the capture volume. The left section shows that the capture volume, 12 mocap cameras are circled in the blue and 3 RGB cameras are in red. We also set up an egocentric camera attached on the head of the subject. The red section sequentially displays the head marker set for tracking the pose of head and the egocentric camera, and the upper body mark set and the hand mark set. I know that you are a little bit tired about the construction process, so I'll give a glimpse on the data and its annotation. Here is the total statistics. The numbers are still increasing. To be emphasized, OakInk2 features the annotation of the object affordance attributes, the demonstration of the primitive task to fulfill this affordance, and the decomposition of the combined tasks that are composed of primitive tasks with certain dependencies. It contains 222 sequences of the demonstration from 5 subjects and 75 objects, including 363 primitive task sequence and 264 combined task sequence. This sequence contains 4.0 million frames, more than 10 times larger than the version 1 of OakInk dataset. In this slide, we will make a dataset comparison sheet. We made a comparison between the OakInk2 and the existing represented hand object dataset. We first compared OakInk2 with the dataset like the APIC kitchen, 100 and Eagle 4D. So they are larger scale and more diverse. OakInk2 provides the 3D grounding information and the former hand and object pose annotation for current learning method. We then compared OakInk2 with the OakInk, a recent dataset focusing on biomanual interaction on the articulated objects. OakInk2 has a comparable scale and contains more frames. OakInk2 covers long horizon hand and object interaction and provides task decomposition for complex tasks. We then compare OakInk2 with the previous counterpart OakInk1. We are much larger scale and covers affordance-based interaction compared to the version 1. In summary, OakInk2 extends the methodology of the OakInk1 to the further front. Here comes the most exciting part. What we can do with this dataset, it is application. OakInk2 provides a specification of primitive tasks based on the object affordance, attribute, and the dependencies for this task in a complex task manipulations. With this data, it is possible to study the potential application of the OakInk2 in the concept-driven embodied artificial intelligence. We name this application as the concept programming. Concept, or the manipulation concept, is roughly recognized as the mental representation of words in a sentence. In previous lecture, however, concept programming, it is to generate the cognitive programs for the concept to complete a complex manipulation targets. Unfortunately, there is no widely accepted definition for the term of the manipulation concept. Therefore, in the OakInk2 version, supports the concept programming by instantiating a new definition for the concept. We define the primitive task as the embodied concept. This concept works as a building blocks to program a complex manipulation target and can be learned by the neural network models. Then, combined tasks are bound to the embodied concept. They contain information about the dependency working as a natural constraint. The program word is encoded in the dependency graph and can be fulfilled by multiple sequential operation paths as long as the constraints are satisfied. In the OakInk2 dataset, Both primitive and combined tasks have paired with the human demonstration and support potential transfer to the robotic demonstration. I will show an example later. Therefore, to accomplish a complex task, the agent needs to actively program the order of the concept. For example, given the scene description on the top left of the corner and a task description, prepare a sweet pear soup in the yellow teacup. We will illustrate each concept on while a human demonstration. For example, the initial state is the pear required for the task is not cut yet. Given the precondition, the next concept that needs to be programmed is the cut something, cut the pear with a knife, and place it into this bowl. This program will continue till the task is complete. Here, we show some concept of the manipulation on the left panel. The embodied demonstration of two certain concepts on the right. Let's play it. Okay. These two concepts are kept the can lid and spread jam on the bread with this spoon. We show the raw image, the annotated simple body, and the robotics hand. Given a complex task, embodied artificial intelligence needs to learn the concept programming based on the given human demonstration. This concept, the concept for this task is an ordered graph. For the specific embodied agent, like a robot, it only needs to perform the per concept imitation learning. And in the next stage, I will show a video to conclude the idea of the concept programming. Oh, sorry. Let's play. Okay. I suggest that the audience can focusing on the concept flow illustrated in the center. The first concept is unscrew the bottle and pour the water out, then screw the bottle. Each concept that are highlighted are the current concepts that the human are fulfill this concept by doing the demonstration. Okay, we are reached the end of the video. And the task is completed. We wish this dataset can support both two words. For the perspective, the AIGC to support the motion datasets, especially the text-driven or the task-specified motion datasets. For the perspective of the embodied AI to support the dexterous complex task manipulation while the imitation learning. We published the extended abstract on the link below, and the OakInk version 2 will also released on the website on the right. Thanks for your listening. And I leave it next time for Q&A. Thank you.
Thank you.